Okay, so we left off trying to find the acceleration. And by the way, I'm sorry this video is really long, but again, it's a 10-part question. So we can substitute, and here we would have acceleration is negative initial velocity over time, right? So you should write that. And we find that that equals negative 12.57 over 1.54. And that all equals negative 8.13. And it's really necessary to keep the acceleration negative, and you will see why actually right now. Okay, so we can use this and some more information. I think the 12.57 number to figure out the distance, which is what we were looking for in the first place. So let's see. We have distance equals, I think, initial velocity times time plus 1/2 at squared. So let's see. Using all this, we can say that distance, and using the numbers we had initially, let's say we had 12.57, positive because we assumed this was the positive direction, times 1.54 plus 1/2 negative 8.13 times 1.54 squared equals distance, right? So if we kept this positive, we would have gotten a greater value, and that would have only made sense if the object was accelerating. So this just doesn't, you can't say that the acceleration is positive. And that's quite a throwback, right? So you just throw all that into your calculator, and you get that the distance traveled was 9.715 meters. This may be slightly different from your answer, because again I used the exact digits, but nobody cares, so yeah. If there's one thing to love about physics, it's that nobody cares about significant figures. And I just said, because I was, done with this long equation, I just said it's reasonable given the data. You might want to write something more in depth, but do whatever you want. Again, let's see. Let's move down to the final part of this question, J. So J asks, how much energy was lost as the bullet was lodged in the block of wood? And you first just be sure not to assume that there's no loss in kinetic energy. There is. Let's see. So what we're going to do here is, first of all, we're dealing with kinetic energy, and we don't have the values for the kinetic energy. So obviously we're going to need to convert our masses and velocities into the energy, right? So we're going to use the equation for kinetic energy, and then I wrote this sort of equation. So what we're going to say is that you have one frame of reference. You have the block of wood, and the bullet beforehand, and then you have the combined block of wood and the bullet, those two combined afterhand. So you have the energies of the two beforehand and the energy of that one thing after, and you're looking for the change from the before and after. So what I did is I said, how did I find that change? Well, these two aren't necessarily going to be equal. These two parts or snapshots or systems, whatever you want to call it, they're not necessarily equal to each other. So I just threw in another variable there, and I said that these two frames are equal to each other if you add this. This K represents the difference between these two systems. Like if you subtracted this amount here from both sides, you'd get the energy from this system 1 minus the energy of system 2, because this is one system. Okay, so then you plug in or you substitute the amount, and you get 1/2.15 times 440 squared equals 1/2 5.25 times 12.57 squared. Now that I'm thinking back, it might have been possible for the last equation, for the last problem, we might have been able to use the coefficient of restitution because it was an inelastic collision, but it's too late, if that's even the case, if we can use that. But anyway, so you calculate this to be 14,520 equals 414.8 around plus K. So you get that difference to be around 14,105. And that's our answer. So for step 4 of J, the final problem in this, or the final part to this abominable question, is 14,105 joules. Does this check out? Does this make sense? Well, let's think about that. Or let me, in my case, read exactly what I had from my paper. I said it does make sense for a system so big to move, or the second system here, there must be a great loss in energy. Because velocity matters more than mass. So when you have a large change in mass, so it's becoming a lot greater, you're going to have the velocity change quite a lot too. And since the velocity is going a lot lower and the velocity matters more to calculate energy, there's going to be less velocity. There's going to be less energy, sorry. So yeah, that is the answer. And that's FRQ question 7.